being recorded, so I guess one, don't claim any results that you can't give a full proof of, and two, the microphones in here will pick up questions, but if you have a particularly long and detailed question, then grab a microphone, so we definitely capture that on the recording. So our next talk is from Deeparnab, who's going to talk about shaving.
Weighing.
And
Thank you.
Okay, personal health care.
So thanks. Thank you to everybody come here, and especially the organizers to invite me. So this is a talk of maybe a failure. So I'll not talk much about it. Started off by trying to understand something called submodular function minimization. It's not important if you don't know what it is, but the state of affairs is something which I think will improve very soon. We don't know how to prove anything lower bound the trivial n, where n is the size of the universe. And that's what we started off thinking of. And we look at a very basic example, and this talk is the story of that example. So here's a very basic question. There's an unknown undirected graph. You know the set of vertices. You don't know the set of edges. And the access to this graph is going to be via the cut queries. All right. So you want to query you can query any subset of vertices, and you get to know how many edges are in the cut set. So exactly one endpoint in this set. You get to know the number. And so this function, as a function of the subset, is a symmetric submodular function. This is a very special case of that. And what do you want to do? Okay, so this is the version I'll be talking about mostly, but there is also a weighted version where actually the edges might have some non-negative weights, and instead of getting the number, you get the sum of the weights of these edges. So that's another access, that's the weighted version. But what do you want to do? You want to determine if the graph is connected. Okay, that's the basic question. Or a slightly more involved is maybe you want to find the maximal spanning forest of this graph, all the connected components of this graph. How many queries do you need to do that? Is the question clear? So this is the query access. Okay, so let's sort of see what the basic algorithms is, and then we'll start shaving. So a warm-up here is an observation. Using the cut queries, you can do the following. If I give you any two disjoint set of vertices S and T, I can find out how many edges go from S to T. So that's a cross query. So cross query is how many edges are going from S to T. How do you do that? You cut of S, cut of T, cut of S union T, you do some subtraction, halving, you can get that. Okay, so that's the primitive we're going to use throughout. So given any two subsets, how many edges go from S to T? That's what you can count with 3 queries. And so what does that immediately tell us? It immediately tells us that I can learn the whole graph in n choose 2 queries, or order n square queries, because if you have any two vertices, you get to know if there's an edge or not, making 3 cut queries. So that's an n square. You can learn the graph and you can solve any problem you want after that. But that's too much. So the idea is, if I don't want to learn the graph, I just want to figure out, say, the spanning forest. Well, you can do, you can do better. So here's a thing you can do. If you fix any vertex, like this green vertex up here, you can find one edge incident to it, if there is any, in just log n queries using binary search, right? So you can ask if there is an edge from this to the everybody else. And if the answer is yes, you halve it. And if the answer is no, you go to the next half of the other half, and you go on and you can find an edge like this. So you can do log n, it's basically binary search, and find one edge. And once you've found one edge incident to a vertex, then you can learn a spanning forest by using a favorite depth first search, breadth first search, whatever you want, in n log n. Good? Yes. Yes, so right now these costs are just 1 for us, and any subset size is also 1 for us. So it's again, the motivation is from submodular function minimization, where every query was equally just cost $1 for every query. Okay, good. Now, if you stare at this algorithm, you'll realize that we really did not need this strength of cut queries. You can just get away with what I call a 1-bit query, where just given a subset S and T, tell me if there exists an edge between S and T. Instead of the number of edges, just tell me the bit 1 if there exists an edge, or if If not, then tell me the answer is 0. So this is called in the literature a BIS, a bipartite independent set query, the BIS query. And it's you just needed that to run this binary search algorithm. You really did not use the fact there are 7 edges between S and T. Just needed what that was. So just 1 bit. And why am I saying this is because if you look at this 1 bit thing, then oh, another thing is that if the graphs have weights, also this would work. But the reason I said the 1 bit thing is actually if you work with only this 1 bit thing, that algorithm is basically optimal, at least for the problem of finding the spanning forest. Why? Because if you're finding the spanning forest, you are definitely finding the connected components of this graph, but there can be like roughly n to the order n connected possible partitions, possible connected components. You are getting 1 bit of information per query. So if you just do information theoretically, you need to make n log n such BIS queries. In fact, even for connectivity, like where you just want to discover the graph is connected or not, it is this is more non-trivial. You can actually prove that if you are deterministic, which the previous algorithm was, then with these 1 bit queries, n log n queries need to be made. And this is basically follows from a result where if I have an undirected graph and half of it is given to Alice and half of it is given to Bob, and they want to communicate to figure out if the graph is connected or not, then deterministically, they need to make n log n bits of communication, and you can use that to get the same query lower bound. At this point, I should say it's an open problem to figure out what the randomized complexity of this is for a while. So Alice and Bob have 2 halves, and you want to decide if they are connected or not, and succeed with probably 2/3. Best upper bound is n log n, lower bound is still n. Okay.
So there's nothing non-trivial
Nothing for the for which one, the connectivity or the communication? Yeah, that has been open since the 80s. Yeah, there's this gap now. It's a nice problem indeed. But with queries, with this cut queries, you actually get log n bits of, possibly log n bits of entropy, because log n bits of information, right? You're getting the number. And so you only get an omega n lower bound. And what we will show, the agenda for today is to actually show that you can shave off this log n from this n log n using these numbers that you get. So the agenda for today is to show an order n algorithm for finding a spanning forest of this undirected graph. It will be a randomized algorithm. It will be a 0-error randomized algorithm, and this will be number of queries made in expectation. Yes.
that the graph is connected. Find a spanning tree. What happens then?
Nothing better than this. As in with the communication or the query complexity.
Well, query complexity first, I guess.
Yes, this is as in I don't see how that information helps me any better. So we'll get. So this is the information theory optimal we'll get. Yeah.
The algorithm was very quick. Like you said, how to find an edge. How do you find the forest?
So once you find an edge, then you can contract that and find another edge from the, like do a DFS from that component, because you have the ability to query any subset S to any subset T. Is that?
It's clear, yeah, but you didn't. Yeah.
I did not. So once you find an edge from any vertex or a super vertex, and after that you can run any depth first search thing.
If you want to find a spanning tree, then there should be omega and log n lower bounds for all of this, even randomized. No, it has n log n entropy, the spanning forest itself.
Yes. So this part, it is n log n. This, just deciding whether it's connected or not, we don't know.
Decision, but not final.
Yeah, the connectivity is decision. Yeah. Good. Other clarification questions before? Yes.
For the spanning forest, the lower bound only holds if you're not given the information that is connected, right?
Correct. That's yes.
Is there a different lower bound for spanning tree? Like you said, there's no better algorithm, but is there any sort of lower bound? If I give you the information the graph is connected, I just want to find
With query complexity? Or? So I don't see, just finding the spanning tree you're saying is going to take n log n queries. Because
That I don't, one bit query, yes. I mean, you have n to the n as spanning trees, so if you want to find it, you need n log n bits to that.
so you hide a spanning tree and you're just trying to find that. Okay. So this is what I want to show. So before the tool that I want to show is going to use this problem called coin weighing. So slightly getting away from graphs. I have an unknown Boolean vector, and what I have access to is if I can query a subset of these elements and get how many ones are there in that subset. Okay, and I want to make as few queries as possible and learn X. So why is it called coin weighing? It's sort of there are n coins. Few of them are counterfeit. Counterfeit coins have weight 1, and non-counterfeit ones have weight 0. You have a scale where you can put some coins and get the weight of coins in that thing, and you want to figure out which the counterfeit coins is. So clearly, you can do this in n queries. You can just take every coin and ask whether you are counterfeit or not. And if you think about it again. Information theoretically, you will need at least n by log n log base 2n queries, because there is n bits of uncertainty in X, and everything is giving you log n. So just as a show of hands, how many of you have seen this problem before, and what can be done? Right. So maybe the main thing to take away is basically there is you can actually get n by log n upper bound. In fact, there is, and you can do it non-adaptively. So there is a 2n by log n, roughly 2n by log n, 2n divided by log n by log n matrix, 0, 1 matrix. So that if you hit that matrix with X and get AX, just AX, using AX, you can recover X. Okay. So you can make 2n by log n weighings. There are 2n by log n different subsets, so that if you ask X of the summation Xi of I in S of for those subsets, those rows, you get the answers, you can figure out X. These are old results. In fact, it's not too hard to show that this existence by just a probabilistic argument. Just take a random matrix. All you need to show is if I give you two different vectors X and Y, AX minus AY will be, AX and AY will be different. You can show it, but what is very nice is there are constructions of these matrices which are efficient. So given AX, I can recover X really fast in almost linear time, linear in n. And this was known from the 60s. There is a gap between n and 2n. And if you stick to non-adaptive algorithms, also this is not too hard to show that you will need 2n by log n. But it's a big open question whether this 2 can be removed using adaptivity. So this is a sort of an aside which has been open for, well, these many years. We don't know the answer. So that's actually quite an interesting. Even with 2 rounds, we don't know of tools to say that this can be bigger. I'll not say anything more about coin weighing in this talk. What I would like to do is to just show how to use these results to get the spanning forest kind of algorithms. I'll say maybe one more thing, another thing, which is another exercise, cute exercise. If I have to solve the coin weighing problems, but I have some more information. If I know that the number of ones or number of counterfeits is small, then you can actually do better. So, for example, if I have just one in the X vector, and I want to find this coordinate, then actually there is a log n sized non-adaptive algorithm. And this is really, you write the, so there are n coins. So you write the numbers 1 to n in binary as the columns. And that's your log n by n matrix. And the claim is that if I hit with a unit vector here, then it will just tell you which coordinate is 1, right? So if this coordinate is the only one, the answer to AX is precisely going to be light up that ith coordinate. So if there is only one entry, this X had exactly one entry, which was 1, then there is a log n by n log n query algorithm. And in fact, if there were D entries, if you knew that or at most D things were 1, then again, probabilistic method, you can prove that there is a matrix of size D log n by log D, where exists this algorithm. it is open to actually find an efficient matrix, an explicit matrix for this, which can be decoded efficiently. But if you allow adaptive algorithms, then you can actually get this query time. Okay, so if you have more information, then you can actually do better. So this is also a result. Okay, how is this related to graphs? So this is one thing I want to maybe say. So let's look at the simplest. So this is I think the reference is missing. So this is a result of Grebinski and Kucherov from 2000. So the problem is this: I have n cross n. There's a hidden perfect matching between these two vertices. You don't know where they are, and you again have these cross queries. You can take a subset S on the left, subset T on the right, and get how many edges there are. And our goal is to reconstruct the matching. So I claim this can be, then I'll show it to you that this now can be done in 2n queries, 2n plus small n. So that's the number of vertices. So let's how. So here's the way you do it. So that vertex V on the left wants to know a neighbor. It has exactly one neighbor on the right, and it wants to find it. So you can think of it for that vertex, there is a vector, which is the incidence vector, which has exactly 1, 1. So there's an n-dimensional vector, which is exactly 1, 1, which is where I have an edge to, and I want to find it. Which means that there exists a log n subsets S1 to Sn on the right side. So if V knew how many edges V has to Si for each of these log n, then I will know where my vertex is. This is exactly the protocol that we saw earlier. The key observation is that these subsets don't change vertex to vertex. So in particular, what we need is for each of these subsets on the right, S1 to S log n, I want to know, like for example, this subset, how many vertices on the left have an edge to it. Yes, Sohail? Yeah, yes, I'm promised the graph is a perfect matching. Yeah, so I want to just learn this hidden match. It's a simple problem. So this is what if we figure this out for each of these log n sets, how many, which are the vertices on the left that connect to it, then game over. Then I can find the match. Okay, now fix a subset Si on the right. What do we need? We need to find its neighbors on the left. So think of it as a vector learning problem. There's a vector X. Now it's on the indexed by the left vertices, where the jth entry is 1 if the jth vertex has an edge to this subset Si. Okay. So for example, in this case, the vector is 1, 0, 0, 0, 1. I want to learn this vector. And now you observe that if I want to do a sum query on this vector, which is I take a subset on the left and I ask how many of them have neighbors to the vertex, to this subset, fixed subset, green subset on the right, well, that's precisely a cross query. So I can do a sum query on this vector on the left, which is the vector that I want to learn, using one cross query in this graph. And now this sort of Lindstrom-Cantor-Mills algorithm says I just need 2n by log n sum queries on the left. So I can learn this vector xi in 2n by log n queries. This is for a one fixed set. There were log n sets. So in total, I can get the whole information that I need to reconstruct the graph in 2n queries. Questions? It's a beautiful algorithm. It's so this was the start of this whole thing about learning graphs using these cut queries. Okay, so it just yes. So because the coin weighing thing is efficient, it's an efficient. It's fast. Everything carries over. This is beautiful. Yes. You mean probabilistically? Yeah, I think you can figure out that they will also work. But this is just fully deterministic, efficient, non-adaptive. This whole thing is non-adaptive. It's as good as it gets. So one thing, so since you asked Sohail whether I'm promised a perfect matching or not, actually you just needed, if you think about it, only needed the left side to have a matching. Like the right side could have collisions and still work. And that is going to be important what is coming out. So we only needed the left side to have exactly one edge, which is they're trying to find.
Like, you could have hoped to think of like the entire vector of edges as like a sparse vector and try to apply the going problem to it, but then the queries are not exactly.
Exactly. Yeah. So it's not. So the queries are a little curtailed. You cannot take any subset of slots and ask how many edges are there. Good. Okay. So this was the beginning of this learning graph. So Grabinsky-Kucherov's paper. So they have they generalize this to learn d regular graphs in nd time, where d was a constant. And then of course, if you just focus on one vertex and learn use the coin weighing for its neighborhood, you can learn in n square by log n time all these graphs. So these are unweighted graphs. And so this there was a flurry of work. And so current state of the art is the following. So if I tell you that the graph has at most m edges, then you can learn any m edge graph using m log n by log m query algorithms. The thing to keep in mind for now is if m was c times n, if the graph was sparse, then you need c prime times n queries. So you can learn sparse graphs in order n queries. It also works with weights. There is an asterisk there because it's a probabilistic algorithm that is efficient. And B, and this is maybe in line with what Graham started with, I actually don't know the proof because it's not there. So there was a conference version which promised a journal version which has not appeared yet, right? But the existence is just a probabilistic argument which is fully there. So if you ask me what's the algorithm with the weights, I won't be able to tell you. Yes? Degenerate, like you mean constant arboricity? Off the top of my head, I'm not aware of it. Okay, so I did not promise matching. I promised spanning forest. So let me show you this work of Apers et al. From 2 years ago, which actually learned a spanning forest in order and Las Vegas queries. The algorithm is very Borufka style algorithm. What you want to do is from every vertex find a neighbor. Then I want to contract and repeat. Okay, so it will run in phases. In each phase, so the things in the left are not connected components, or rather representatives from every connected component, and there are 2T connected components in all. And in each phase, every representative from a connected component will try to connect to another connected component. I want to spend order T queries, okay, in expectation. And I want to shrink the number of connected components to some constant times t, Ct, where c is less than 1. If I'm able to do that, then I'm done by geometric sum series, right? So that's the Borufka style algorithm. So we are going to just do one phase. In fact, we're going to think of these things as singletons. Okay, good. So this is how it starts. First, this step is maybe not super important, but it randomly recolors the graph vertices red and blue to make a bipartite graph. And with constant probability, a red vertex will have, if it had any edge to begin with, it will have with constant probability a blue neighbor. Okay? If it does not have a blue neighbor, then I'll just throw it out. Oops. So this is the random recoloring. And what's the goal? Every red neighbor, I would like to find a blue neighbor. If I can do that, then I can contract, and I'm hoping to get this true for at least half the nodes. Okay, here's the algorithm. So we bucket the red vertices with respect to the number of blue neighbors. Okay. So I am asked for, so the bucket I on the left are all the red vertices which have roughly 2 to the I blue neighbors. How do I find the number of blue neighbors? Well, I just take the vertex S on one side and all the blue vertices on the right side. It's just one cross query. Okay. This is true only because the graph is unweighted. I can find the degree or the number of neighbors with one cross query because the graph is unweighted. And then what I do this trick of subsampling. So for bucket I sample vertices, blue vertices with probability 1 by 2 to the I. Okay. So bucket I, red neighbors at 2 to the I vertices, blue neighbors, and I'm sampling at rate 1 by 2 to the I. So what is true with constant probability, this bucket I red vertices have exactly one neighbor in BI. Right? Because I have 2 to the I blue neighbors, I'm sampling at rate 1 by 2 to the I. With constant probability, I will have exactly one neighbor, and I can check it by making another query. Do I have exactly one neighbor? If I don't have one neighbor, I throw it out. And what will remain are omega t vertices on the left, which have exactly one neighbor on the right. So what is on the right? I only store the BIs. So B1, B2, B3, I store the union. So I have now an unknown graph with omega t vertices on the right, left. T was the number of components. T is the thing I'm trying to shrink. T was n. To begin, in the beginning, T was n. So I have the situation now after sampling. There's an unknown graph, and on the left I have omega t vertices. Right, I have also t vertices at most, with the promise that every vertex on the left has exactly one neighbor on the right. There can be collisions on the right, but this previous algorithm can learn the whole thing in order t queries. So in order t queries, I will shrink these things. The number of connected components went from t to some ct, which is less than 1, and then I'll just recurse. So that's the order n algorithm. Okay. So the place where there was the Las Vegas style is that if I have too much shrinkage, I just repeat the experiment, and I can check it. It's provable. So there is no error there. It's just that I might have to do it a little more.
So wait, so the randomization was in the coloring?
Yeah, the randomization in the coloring and the sampling, but this is the more important.
You would have probably got rid of that randomization. Of the coloring or
Not clear. How much time do I have, Azhar? Some. Okay, some is good.
some of what?
Sum of max. Okay. Good. So let me say a little. So this was a paper of Papers et al. But as I said, the number of blue neighbors of a vertex was possible because the graph was unweighted. But if I have weights, this was the result. So if I have weights, then this step is actually not clear to do. Okay. So now imagine. So the graph now has the edges have weights. So when you query a vertex and a subset, you don't get the number of edges. You get the sum of weights of these edges. So you have no idea if you have a million edges with weight 1 by million or one edge with weight 1 when you get the answer 1. Okay, so you cannot do the bucketing on the left. So you could think about, okay, let me try to estimate how many neighbors I have. For example, maybe this vertex here is trying to estimate the number of neighbors, and all it gets is these sum queries to the weights. So it's a question of estimating the support of a vector using sum queries. So I have a vector, non-negative. I want to estimate the support using sum queries. What can you do? Well, there's a recent paper which says that actually you cannot get in omega 1 queries, you cannot estimate the support up to a constant factor. You can estimate with a log n queries where n is a dimension, and this omega 1 is actually omega log n, but maybe the true answer is log n. But if I don't want an n log n algorithm, actually the truth is we found an n log n algorithm, but we want to shave that n log n as well. So I want to show a way of sampling that my student found, which was sampling from the right instead of from the left. So, or rather, not looking at the degrees at all. But the main tool here was used instead of Grebenski-Kucherov. The tool is to say use that the sparse graphs can be learned efficiently. This was the idea. So let me and maybe tell you this algorithm. So here's the algorithm now. It's a weighted graph. So I'll not be able to figure out how many neighbors a red vertex has on the right side. But here's what you do. It's actually simple in hindsight. So you run in phases. Phase 1, you sample like very rarely from the right side. So you sample vertices, blue vertices with probability very small, 1 over n. But whoever you sample, you learn the whole graph to the left. Okay. Is this going to be a sparse graph? Yeah, because there can be at most n edges, right? So because I sampled very little vertices on the right, this is going to be a sparse graph, so I can learn it. And once you learn some edges, so this vertex is connected to these red vertices, then you throw these red vertices away. I found neighbors from these red vertices. So the next time I sample B2, I only learn the graph between B2 and the remaining. And I throw what I learn away and I continue. Okay. So what's the worry? The worry is I'm not throwing away red vertices enough. So maybe I'm sampling at right 1 over root n on the right. So I should root n vertices on the right, but actually even then there is theta n vertices on the left, and I have a dense graph, and I'm screwed. That's the worry. But here's the claim that actually the expected number of edges that you learn is only going to be linear. Okay, so this is, so you are sampling at rate 1 by n, 2 by n, 4 by n, 8 by n. Every time you're sampling, you're learning the whole subgraph on the right. Whoever you learned edges to on the right, you throw them away, and you're just sort of storing all these edges. The number of edges is only going to be linear. Is that claim clear? Okay, and why is the reason? Again, the reason is again the same idea that if I have a degree d and I'm sampling at rate 1 over d, I will have one edge, except I don't even need to know d. So here's a sort of a maybe sketch of a proof. So fix this vertex and suppose it had 2 to the I edges, and look at the probability that this edge is present, right? So I have 2 to the I edges. So on the right side, till I sample at rate 2 to the 1 over 2 to the I will not touch any of the edges. And when I do sample at rate 1 over 2 to the I'm going to sample one of them, and the remaining, like in its neighborhood, I'll be uniform. And once I learn one neighbor, this vertex will never come again. So basically, from every vertex, only one of the edges incident to it will be present. But I don't need to know it's how many edges there were. Exactly. So yeah, so maybe, yeah, so saying it differently, I was worried that I'm at rate level root n, and then there are these lots of vertices on the right which have high degrees to them, but the high degree vertices have already been learned and thrown away. So I don't need to know the degrees and really mimic the previous idea. So yeah, that's what I wanted to say. And using this, you can actually now get the following, that even on a weighted graph, you can make order n cross queries and expectation and learn a spanning forest. So this will also not work for your lower bound if you wanted to. So let me end with some final thoughts. So one is that we can solve connectivity in undirected graphs in order n cut queries. So that's not your candidate for submodal function minimization lower bound. It never was, but it was curious for me at least to figure out this gap between n log n and n. But the main hammer, which I did not know about, was this coin weighing trick of Lindstrom and Cantor-Mills and others, which might be useful. And it's known in various names in various settings. It's called quantitative group testing or k-separating matrices. So it's, I think, a good tool to have in one's arsenal. The Apers et al. Paper actually could solve the exact minimum cut problem, not just whether I'm connected or not, but find the exact minimum cut in unweighted undirected graphs and order n queries. This is a Monte Carlo algorithm, so it has an abort probability. And so there are lots of things open here we don't have any idea about. For example, what about weighted graphs minimum cut? There was a very nice paper of Mukhopadhyay and Anonkai which can do it in n polylog n. You can do all these cut sparsifiers in n polylog n. So if you allow me this extra polylog n, many things can be done. Are they necessary, or can you shave them off? We don't know. But the things are much more much less understood if I look at directed graphs. So I have a directed graph and I want to know if it's strongly connected, and what access do you have? I have a subset S, and I get to know how many directed edges are leaving that set. The directed cut query. I actually don't know anything better than something like n square by log n. So even this is quite open. Hypergraphs also, I can do connectivity of an undirected hypergraph in n log n. Can I shave that n off? Log n off. I don't know how to do it. And exact min cut also, I don't think people have looked at it. So that's also completely open. So yeah, lots of things to be done here, but I just wanted to share this cool trick of coin weighing. Okay, thank you.
This big hammer that you can learn any graph of m edges in whatever time. So first, how complicated is this big hammer? And secondly, do you have to use it?
So this was only for the weighted graphs. So that's a good question. So how complicated is, so the exact m log n by log m, which is the probabilistic efficient algorithm, I actually don't see the whole details. So there was an asterisk. But the proof, existence proof, is not that complicated. I mean, it's a probabilistic calculation which has been done. And that's in a different paper of Bashuti and Mazawi. There is a deterministic algorithm which is m log n by log m plus m log m. And that is actually building on these coin weighing things plus an extra binary search. It's a clever thing, but the main, again, the main hammer is to learn these n vector vertices in n by log n. That is, yeah, it's actually not that difficult. So if you allow an extra log m, you can get this. But the choice result, I don't see the full details.
Is it necessary?
That part is harder for me to say. I don't know. Yeah. So can it be? Can this idea of sampling be bypassed by just using some matching learning? I don't know. Yeah.
So you can think of the cut queries as having like x transpose a y axis where x is a discrete set. If you allow real vectors, do you think, let's say you're in a model where you can query real vectors for x and y, would that gain you any power? Do you think?
And you give me for free?
Yeah.
Yes, then you can do many things. So, for example, the coin weighing problem, you can learn the whole thing in one query by just doing powers of 2. So you have to sort. If you restrict the bits that are there in the weights, then
Okay, yeah, let's say you give a lot to you're restricted bits.
So I think you can get that how many bits you're using in the denominator. Yeah. Just because you sort of have this Boolean matrix and you shrink it at the correct juncture to get the real number or integers. So those things.
What about learning hypergraphs? And I mean, not connectivity, but
okay, good.
You can test if two vertices are connected, of course, but you have no idea what the hyperedge.
Good. Yeah. So I have not. Yeah. So learning hypergraphs using just cut queries is in some sense impossible, the whole hypergraph, because I can give you two simple hypergraphs where the cut queries are all the same, but they are different. But the connectivity is, of course, so I can learn whether a hypergraph is connected or not in n log n cut queries. Right. As I mentioned, but this is simple. Think of the skeleton graph where I just connect everybody, and I can do
or a giant hyperedge. You can't distinguish the two, right?
But the connectivity I can solve, but I cannot figure out the hypergraph itself. Yes, so that's not even directed graph. That's the same issue. You cannot figure out the directed graph because I take a cycle and I reverse it. You will never get to know.
Right.
But the connectivity problem can still be solved.
Okay. What kind of queries would you?
The query is still the same. You are doing.
What kind of query would you need to learn more than just the connectivity?
So there are people who have studied. People study additive queries. So I take a subset S and tell me how many hyperedges sit inside that. Okay. And there are some results, but the results are exponential dependence on the arity.
Yeah. Right.
And that's also necessary at some. There have been works on this. Happy to talk about more, but I just didn't have time. Yeah.
Your algorithm requires log n rounds of adaptivity in that. Can you get that done? Can you do some of that in parallel, or is it inherently?
Yeah, these are adaptive. Yeah, that's a great question as well. It's a whole other aspect. Like, what is the lower bound on, say, 2 rounds? Can you do it in 2 rounds or constant rounds? So I think in polylog n rounds, you can do n log n. Those are, but can you do it in? So our algorithm for learning. Still polylog n, I guess, but I have no idea how to prove lower bounds are constant, or if there exists. I don't know. Good question.
Excellent. Right.
Thank you.